Okay, an imperial Death Star is circling the Earth, this being the center of the Earth right here. It's actually not circling it, it's in an elliptical orbit about it, and they are just waiting for the signal from the chief high lord to to blow up the world. And we have to, of course, shoot that out of the sky. And our intelligence has revealed that when they reach this point in the orbit, and they're heading there now, when they reach that point in the orbit, they are going to be at a weakness because they're going to have to let down their shields to be able to blast the Earth, and that is the exact instant that we have to hit them when they let down their shields. So of course we need to aim here, but that's not all. And if we consider this a two-dimensional problem, and we put, say, the center of the Earth at the origin, and if we had any scientific capabilities at all, we certainly would have figured out the equation of their ellipse by this point. So just finding where the line of our trajectory to blow them out of the sky is going to meet at this point isn't enough in XY. We can't just fire and say, well, we're going to hit the ellipse because we aren't shooting at the ellipse. We're shooting at the Death Star when it gets to that point, which means we need to introduce another parameter besides just x and y. We have to know, if we call this t0, we have to know what time we're dealing with, and that time has to be satisfied as well. And the time that ours is in the air has to be factored into that. So there's a lot more going on than just knowing that this line intersects at that point, what the coordinates of that point. So that is where we move into what are called parametric equations. And the parameter we're talking about in this case is t, or a time element. Let's go ahead and move back one here. Okay, so in a time element, um, so what we have, what we're going to study to get ourselves to the point where we can solve problems like that is what are called parametric equations. And normally we're used to seeing y be determined based on the value of x. But in this case, x and y are both based on the value of t. And you may be saying, well, I understand we have an x-axis, we have a y-axis. Where's the t-axis, or is this a three-dimensional curve? Not so much. We're still dealing in the xy coordinate system, but time is going to be the deciding factor of the value of x that correlates to the value of y. So we're going to create an expanded t-chart. In this case, t is going to determine x and is also going to determine y. And I'm going to choose some values for t until I get a good feel for what the curve is going to look like. So I'm going to choose t to be 0, and when t is 0, x becomes absolute value -1 or 1. And y becomes 0 plus 2. T is 0, 0 plus 2 or 2. So we have an ordered pair. Doesn't have anything to do with 0, has everything to do with 1, 2. We have an ordered pair at 1, 2, and we may want to put a notation next to that. What is our point? What is our time at this point? Our time at this point is 0. That may become useful for us somewhere down the road. Okay, so now I'm just going to pick some other values, and seems like this should be a pretty interesting graph around when t is 1, because that's when the absolute value starts to come into play. When t is 1, I get absolute value of 0, and when t is 1, y becomes 0 plus 2, or 2. Excuse me. When t is 1, y becomes 1 plus 2, or 3. So we have a point at 0, 3, and we hit 0, 3. You may want to mark that when t is 1. And likewise, I'm going to continue on for a couple of points. When t is 2, I get absolute value of 2 minus 1, 1. When t is 2, y is 2 plus 2, or 4. So I have a point at 1, 4. And hopefully right now, I just realized something about parametric equations. even though they're written as functions, this would be a function, this would be a function. The result is not necessarily a function because you can clearly see that at time 0 and time 2 on our graph that we would not pass the vertical line test. Okay, let's continue on, see what kind of values we get. When t is 3, when t is 3, I get absolute value 3 minus 1, or 2 for x. When t is 3, y becomes 5, and I have the point 2, 5 when t is 3, and I'm beginning to get convinced that what is going to happen is we're just going to continue like this. And let's go back, take a look what happens when we go to time to the left of 0, or time prior to 0. For instance, time -1. What happened 1 minute ago, 1 second ago, 1 year ago, whatever our time unit is. So when t is -1, I get absolute value of -1 minus 1, -2, I get 2. And when t is -1, my y value becomes -1 plus 2, 1. So I get the ordered pair 2, 1 when t is -1. And at that point, I'm becoming convinced that here's what we're dealing with. And that is our equation. Wouldn't want to say that that's our function, or excuse me, that is our graph. Certainly wouldn't want to say it's our function. And this says sketch the curve and indicate the orientation. The orientation is just asking for what direction is this particle moving. And since here is time 0 right here, this thing is moving in this direction. It's moving up and left until it gets to time of 1, and then it turns and moves up and right at that point. So there's an example of a parametric equation, and maybe the graph's somewhat surprising, but that is a process for getting our graph. Okay, let's take a look at another one of these. Okay, here's problem 14. Maybe a little bit simpler. We don't have an absolute value in there. So I'm going to go ahead and set this guy up the same way. I'm going to choose values of t so that I can figure out appropriate values, ordered pairs, x and y. And I'm going to start with 0. Very often parametrics would start with time equaling 0. Of course, that would make some sense. But sometimes we deal with time in the future or time in the past. So if t is 0, I get for x 3 minus 2 times 0, 3 minus 0, 3. For y, I get 1/2 times 0, or 0. So we have a point at 3, 0, and we might want to notate that that is when time is 0. So I'm just going to continue on, find some points at time 1, time 2, and see if we get comfortable with that. When t is 1, I get 3 minus 2 times 1, 3 minus 2, 1. When t is 1, y is 1/2 times 1, 1/2, and I have a point at 1, 1/2. And that is when t is 1. So I'm just going to continue increasing time. When time is 2, 2 days, 2 minutes, 2 years. When time is 2, I get 3 minus 2 times 2, or -1. When time is 2, y is 1/2 times 2, or 1. And at -1, I'm up 1. So when time is negative, or excuse me, time isn't -1. When time is 2, I'm at the ordered pair -1, 1. And I see those are in a line. I might need just a little bit more convincing, so I'm going to go to 3. When t is 3, x is 3 minus 2 times 3, 3 minus 6, -3. When t is 3, y is 1/2 of 3, 1/2. So I have a point at -3, 1/2. And now at this point, I am very convinced that as I move to the left, or as I increase t, perhaps I should say, it looks like we're going to be in a situation where we have a line. And it may stand to reason that as we move to the right, the line continues, but let's find one point to the what I'm saying to the right, but when time goes backwards to say -1. When t is -1, x becomes 3 minus 2 times -1, or 3 plus 2, 5. When t is -1, y becomes 1/2 of -1, -1/2. So I have a point of 5 negative 1/2, and the line appears to be continuing there. So this is t is negative 1. Line's continuing, but again, I need some orientation, and that is what direction is the particle moving from 0 to 1? We're moving in this direction. So pretty simple parametric expression, and interesting to note that when my parametrics were both linear, my result was linear. So maybe there's something to that. Okay, here's one that's going to bring in some of our trigonometry, and at first thought, excuse me, at first thought we're like, oh, this could be rough, but I think if we just use our quadrantal angles, if we remember back to cosine graph looks like this, and our quadrantal angles are very, very clearly revealed to us. So there's cosine, and our graph of sine our quadrantal angles are very clearly revealed. Those might be helpful in the use of our t-chart. So let's go ahead. Theta is now our parameter. Theta is what's being used. We would say that x is a function of theta, y is a function of theta. So theta is now our time, or our t element from past problems. So I'm going to choose theta to determine what x is, to determine what y is, to determine what my ordered pairs are. So we'll go with quadrantal angles for starters. If I put in 0 for theta, x is the cosine of 0, but the cosine of 0 is 1. So x is 1. Y is 4 times the sine of theta, or sine of 0. The sine of 0, though, is 0. 4 times 0, 0. So I have an ordered pair at 1, 0. That occurs at time 0. And I'm just going to continue to my quadrantals. We may have to come back and fill in some of the gaps, but at pi on 2. X is cosine of pi on 2, but cosine of pi on 2 is a breeze. If we can picture the graph, we got it. Cosine of pi on 2 is 0. Y is 4 times sine of pi on 2. Sine of pi on 2 is up at 1. 4 times 1, 4. 0, 4. That's what happens at time pi on 2. Let's continue with our quadrantals. So far, so good. When x is pi, or excuse me, when theta is pi, x is cosine of pi, but cosine of pi is negative 1, so x is negative 1. Y is 4 times sine of pi, but 4 times sine of pi is 4 times 0, or 0. So I have a point at negative 1, 0, and that occurs when x is pi. And let's continue. 3 halves pi. At 3 halves pi, x is cosine of 3 halves, 0, 1 half, 2 halves, 3 halves pi right here is 0. And y is 4 times sine of 3 halves pi. Sine of 3 halves pi is negative 1 times 4, negative 4. 0, negative 4, that occurs at 3 halves pi. Now, because there is no horizontal shifting or speeding up of the period, I can certainly expect 2 pi to give me the same values as 0. We're not speeding up the period, slowing it down, shifting it. So this thing is going to start to repeat after that. So now what I got to be concerned with is what's happening on this between these 4 points that we have. Here, 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 and here. What's the shape? I mean, who knows? Maybe it's a rectangle. Maybe it's a diamond. Maybe it's an ellipse. Maybe this line curves in like this. Not so certain. We might have some thoughts about that. So what we might want to do is fill in one gap. And I'm going to say, what happens at pi on 4? Halfway between 0 and pi on 2. Well, a pi on 4, as we all know, we get a 45, 45, 90 right triangle that we could have sides of 1, 1, and root 2. So at pi on 4, x is the cosine of pi on 4. The cosine of pi on 4 is 1 on root 2, which is root 2 on 2, about 0.7. And y is 4 times the sine of pi on 4, which is 1 on root 2, about 4 times 0.7, about 2.8. I realize we're dealing with a little bit of rounding error, but you're going to see my point here. So at 0.7, I am up at about 2.8. I'm in about this position right here, which tells me that I have a concavity. I'm going to sketch it over here like this. So it leads me to believe that we might be dealing with an ellipse here. Now you could fill in a lot more gaps and get a lot more data points, but I'm going to convince you shortly that we are in fact dealing with an ellipse. Okay? So pretty nice way to represent ellipses if this in fact is an ellipse in this type of form. Okay, so let's take a look at another approach for this by eliminating the parameter. And to eliminate a parameter, I don't want to have theta in the equation. So I look, and what am I dealing with? I'm dealing with cosines of theta and sines of theta. I would love not to have cosines and sines in there. And how can I turn cosines and sines into not trig functions? Well, we know that sine squared of theta plus cosine squared of theta is 1. And so I'd like to be working with sine squareds and cosine squared. So I'm going to solve this second equation for sine. Y on 4 equals sine of theta. And I'm going to go ahead and square both equations. I'm going to square this first equation. I get x squared equals cosine squared of theta. I'm going to square the second equation. Y squared on 16 equals sine squared of theta. And I'm going to add these two equations together, combine them, and I get x squared plus y squared on 16 equals cosine squared plus sine squared 1. Holy smokes, we're dealing with an ellipse here that is centered at the origin. There's our standard equation of an ellipse, centered at the origin. I want to go to the right one, to the left one, up 4, down 4. Right one, left one, up 4, down 4. And that should look pretty familiar unless you have a worse short-term memory than even I do. So there's another approach to this. So why aren't we just dealing with this? Well, we may need to know what value of t are we dealing with to get right there. So maybe more beneficial to know in this case what value of theta gets us into that position. So, but anyway, there's another approach to graphing this. We just don't have our orientation if we're given this equation. On the last problem, we learned that our first point was here, then there, so we would have had an orientation. But the orientation is not clear from this. Okay, so that's called eliminating a parameter. We'll look at a couple maybe easier problems of eliminating parameters along the way. Okay, so here we're to eliminate a parameter and obtain the standard form. Now, you may be asking, what's the parameter? Is it h? Is it r? Is it theta? It is one of those. The parameter is, it would have to either be r or theta. However, for equations of circles, we're familiar with h's and r's, and we're familiar with k's as well. So we're going to try to eliminate theta and see what happens. So again, we're dealing with a cosine and sine. If I could combine those squared, cosine squared plus sine squared, then I could get 1. So I'm going to solve for cosine of theta. That is x minus h on r is cosine of theta. I'm going to solve for sine of theta. That is y minus k on r is sine of theta. And I'm going to square both sides. Square both sides of the first equation. Square both sides of the second equation. and I'm going to add my equations together. So I get x minus h squared on r squared plus y minus k squared on r squared equals cosine squared plus sine squared 1. And at first inspection, we may say, circle, no, not a circle, this is an ellipse. However, this is an ellipse that wants to go to the right h, up k, start at the center, but then from the center I want to go to the right r, left r, up r, down r, and I realize, oh, if I'm going to the right and left as much as I'm going up and down, this really is a circle. Or algebraically, multiply both sides by r squared. Oh, there it is. We've seen that before. So we are used to this being our standard form of equation. We've been living in kind of a XY coordinate world, whereas if we lived in a parametric world, we'd be completely comfortable with this. What's the benefit of this? Well, the benefit of this is we would know when we need to fire to hit the Death Star. You know, we need to know. I don't need to just know about the ellipse. I don't need to know what the ellipse looks like. I need to know when we fire to hit that thing. We have to know the time element because it's not truly an ellipse. It's just an object on an ellipse that we're interested in. Okay. And then 40 says use the results from number 36. So I took the liberty of putting number 36 down at the bottom of our board so we could refer back to that guy. It says to find a set of parametric equations to represent this. Yeah, in non-parametric land, the land we've been living in, we would say this is x minus 2 squared plus y minus 5 squared equals 4 squared. Because here is h, here is k, and of course here is r. But what we just learned about parametric land is that circles can be written in that form. So x is h2 plus r4 times cosine of theta, while y is k5 plus r4 times sine of theta. So that's an introduction to parametrics. I'll be interested to see if there are some parametric equations on the ACT test this year. The homework assignment is on the chapter 4 of the website. However, I'm also going to have it here. You may want to pause and jot this down, save you the time of looking that guy up.